topology appears. And the first question was associated with algebraic geometry. Which we said that if you have a family of polynomials, here for simplicity we assume that K is algebraically closed. You can think about the complex numbers. Then, if we compute the zero set or the variety inside Kn, which is the set of common zeros, such that all these polynomials vanish. Then, when we construct the Zariski topology on K, we can endow this set with the Zariski topology. And when we put here the Zariski topology, this is called the affine space. So this set receives a topology as a subspace, and this is called an affine variety. It's not precisely correct, but for the purposes of these lectures, I think it's okay. But we said that this topological space is bad because topologically algebraic varieties are bad because we don't have the Hausdorff property. So, usual geometric and topological arguments that we do, for example, in differential geometry become unavailable for algebraic geometry. On the other hand, we said that algebraic varieties and Zariski topology are very general concepts because they are available for any field, at least if it is algebraically closed. So, for example, we can think about the algebraic closure of Q. This is a field which is not the usual fields that are the complex numbers or the real numbers. For example, the only field which is algebraically closed is this, but we can construct the algebraic closure of Q, and this is more involved with questions in number theory. And yesterday I said that, for instance, arithmetic geometry, arithmetical number theory algebraic number theory has to be with algebraic varieties over different fields. So it is relevant to study sets of zeros over other fields which are not C and R. C and R are like the classical fields which we always study because they are historically important. Geometry started with the real numbers, then the complex numbers with the Italians, then Calabi-Yau manifolds in physics, then the geometry of space-time, Minkowski space-time. Everything is real and complex. Quantum mechanics is complex. Physics is like one of the leading branches of science that leads mathematics. They have a very strong interaction. So why should I care about another field which is not R or C? So if you are interested in number theory, you may start studying Q. And if you do this, you are going to see new phenomena appearing, which is from different nature than phenomena appearing in R or C. So motivation is that studying algebraic geometry of the other fields is important for other purposes other than geometry, physics, maybe number theory, maybe other mathematical aspects of science. So, if I have K equal to this field, for example, to fix ideas, and if I have an algebraic variety over this field, how can I study topologically and maybe from a differential perspective, from a differential geometry perspective, this object? The answer is, or was yesterday, to look for a topology on the field such that the topology has more open sets. So the answer is finding and refinement of the statistic topology. So this was like the leading question yesterday. How can I improve or get better topological objects from algebraic geometry, not precisely from differential geometry or complex analytic geometry? And the theorem that I presented yesterday was that valuations can help with this. This theorem says that, let me remind you the theorem. Suppose that K is a field and that tau K is a nice topology. Okay. By nice, I mean K together with tau K is a topological field, and it is Hausdorff. Then the result is that this topology can always, or is it coming? It is just coming from an absolute value from all the basic mathematical education. We are going to remind the definition in a moment, or it comes from true evaluation. So, with this, yesterday I wanted to stress the fact that valuation theory on fields is not just a dry algebraic subject, just moving letters and doing algebra, abstract algebra without a link with geometry, for example. But valuation theory, if you understand valuation theory, crude valuations, they give you examples of topologies of fields, such that if you put one of these topologies, I will explain how to get a topology from evaluation. If you get one of these topologies, you can improve the topology of these varieties by changing, for example, let me call here theta B, the topology induced by the evaluation. Then instead of taking the variety with the induced topology of Zariski here, for that here, I have Kn with the Zariski topology. If this topology is final, I can also consider Kn endowed with the evaluation topology. And hope that this topological space, well, this topological space is going to be housed, because the ambient space is housed. So this topological space is better than this one, which is not housed. So I can expect to have more geometric and differential geometric tools to study this set from algebraic nature with this topology than this topology. So this is one of the leading forces of valuation theory and crude valuations of these tropical methods, because after all, these crude valuations are tropical objects, because these are tropical semi-fields. So changing the topology of objects from algebraic geometry is one of the leading forces of behind valuation of tropical things nowadays. Okay, so this is where I left yesterday. And I forgot to mention what are perfect spaces. So yesterday I made an announcement that I was going to keep there the concept of perfect space, but unfortunately I forgot. I didn't get back to this thing. So I will just mention something about perfect spaces, which is a concept in number theory also. So another possibility to study tropical things and crude valuations are perfect spaces. And this concept comes from number theory. Specifically from characteristic theory. What is positive characteristic is, for example, the algebraic geometry that you get from finite fields. For example, F2, F3, F5. Definition, the characteristic of a ring is the minimal number such that if you sum this number of times, it equals 0. The characteristic is R. If I sum R times 1, this equals 0. If this does not happen, then the characteristic is 0. So, characteristic, if R is a field, the characteristic can also be a prime number. This is a theorem. And this is perfect spaces is a positive characteristic. if once you prove that the characteristic can always be prime, this is a prime positive, and this has to be something, a word in algebra such that if you sum 1p times, it equals 0. So, algebraic geometry and analytic geometry and number theory over the word in characteristic P is not well understood. We have too much problems translating all the geometry and analysis from characteristic 0 to characteristic 3. So one of the modern branches of mathematics is to study what happens in characteristic 3. It is one of the biggest branches of mathematics right now. And in 2011 or 12, maybe 2012, a German mathematician called Peter Schulz introduced perfectoid spaces as a means to study the world in characteristic P. And he received the Fields Medal in 2018, if I remember correctly. So, Peter Schulz introduced perfectoid spaces as a means to study. So he won the Fields Medal in 2018 as a means to study geometry and arithmetic in positive characteristics. And the comment is that true valuations are an important part of perfectoid theory. If you don't know crude valuations, you cannot do perfectoid theory. One of the bases to start regarding at this subject is crude valuations. So I'm sorry for not commenting this yesterday, but this was the comment, is that group valuations are well alive.
Are there rings which have negative characteristics?
No. All the characteristics can be 0, a prime number, or 1. This is something new. Perhaps I can discuss this with you later, but this is a new idea. In fact, some people say that characteristic 1 is idempotency. So, characteristic 1 may sound stupid because it means that 1 equals 0, right?
Yes.
Because the minimal number such that you sum 1, this number of times equals 0. But if this number is 1, this means 1 equals 0. But this is the wrong way to think about characteristic 1. The correct way is tropical mathematics. And this is not me saying this. This was said by a very important mathematician whose name is Salam-SMS. But I don't want to discuss this because not all people agree. Sometimes it's the same as with tropical. Sometimes you tell tropical, sometimes the people is very enthusiastic, and sometimes people is like, okay, I don't want to.
I think this result is for integral means ring can have a characteristic which is not prime. I think so.
No, I mean, we are here. Yes, you're right. I mean, rings can have characteristic which is not prime, 0, or 1.
Yes.
But speaking about fields.
Yes.
Sorry.
Okay.
So speaking about fields, classically these are the only
Yes.
possibilities. But what I'm telling you right now is that there is a third, which is new, but is not well accepted right now. Some people are very enthusiastic of this idea, and some people believe that this is stupid. And there is no in between. Either you are with them or against them.
Then why did you write positive characteristic mathematics?
Sorry?
Why did you write positive characteristic mathematics?
Because positive characteristic is accepting this paradigm. And in this case, this is zero, it's not positive. It is positive, it is prime. Any other question? Okay, so let me tell you how can we derive a topology from evaluation. Let's recall our basic properties for evaluation. Maybe I am being repetitive, but I don't care. I just want you to learn this concept very well. So I take V from R to S. Here R is a ring. S is a tropical semifield. And V is a map such that V of 0 is 0, V of 1 is 1, V of A plus B, F times B is A of A times B of B, and B A plus B is bigger or equal than the minimum for B A plus BB. In the general case, I can put here minimum or maximum. Minimum or the plus from the same field. And I told you yesterday that I was able to change the last rule. If I use maximum convention. Now, what if I change V by a bar? What is this? Absolute value. These are the properties of the absolute value.
Yes.
What I'm telling you is that absolute values and valuations are the same thing. We just need to change the symbol. And we know that an absolute value induces a metric, right? If I have an absolute value, so let me change this by bar. How can I induce a distance?
X minus y absolute value. Yes.
And if I have a distance, I have a metric topology, right?
Yes.
Here. So I have a topological space.
Yes.
Very beautiful. Valuations is the algebraic world, but the analytic world is absolute values. So this distance gives me a metric topology, and metric topology gives me a topological space. Metric space and metric space gives me a topological space. But there is something, recall that S is a tropical semifield. So it is totally ordered. And instead of putting this plus, I can put a maximum, right? This is called the ultrametric inequality. And it is stronger than the triangle inequality, which is classical in the complex of the real world. So new topological phenomena appear. Maybe I will discuss some of that later, but not now. What I want you to keep in mind is that an absolute value may satisfy the classical triangle inequality or the ultrametric triangle inequality. And these, in some sense, these are two different worlds. So if A plus B less or equal than A plus B, inside R, this is called an Archimedean absolute value. And if it satisfies it is called non-Archimedean. Okay, so the only possibility to have an Archimedean absolute value is that the absolute value lands here. There is no other possibility. The only way in which evaluation is classical is if it is the classical absolute value. Otherwise, any other valuation is going to be non-Archimedean. Okay? So, examples. Q with the absolute value, usual absolute value, R with the usual absolute value, C with the usual absolute value is Z bar square root, or in these particular cases is X if X is positive and minus 6 if X is negative. So these are Archimedean fields. Non-Archimedean fields we have seen two. The first one is the pairing. Sorry, QQ. So the absolute value of a quotient n over n is P, is the valuation of n minus the valuation of n, or it may be the other way around, it depends on the convention. This is the pairing. And together with this definition, I get the topology, and I can put the pairing topology on Q. This is going to be a different topological space than Q with the usual number. This is going to be non-Archimedean, and this is going to be Archimedean. And the other example that we saw yesterday was Q, X, Y, and here I put Z, Q, and I send a polynomial in two variables to the hexadic order and the y-adic order, or the hexadic degree and the y-adic degree. This is another example of evaluation, and by that I explained there, this is going to be also a topological field, which is going to be high. So you may start looking at the diversity of fields and topologies that we can obtain from algebra. Like, these are the traditional ones. Like every book in geometry and in analysis and in topology, every book assumes that spaces are housed. Perhaps you have seen the definition of abstract manifold in topology. Let's recall it. And let's see how Hausdorffness shapes or brain shapes of science. What is an abstract manifold? This is a concept from topology. Does anyone know the definition? Okay. So it is a pair, well, it is a topological space which is locally Euclidean. But first of all, you need to ask it to be housed, and second, countable. So the first two actions is that this topological space has to be housed, and second, countable. Which means, what means second countable? It means that it contains a countable basis.
Yes,
right?
it is a countable basis.
And the third action is that this should be locally Euclidean. It means that if you have space here, this is called M. For every point in M, you should be able to find an open set containing P and a homeomorphism to an open set of Rn. That's all. This is a topological manifold. But the importance of the definition of topological manifold is that it should be housed on. There is no definition, there is no classical definition of topological manifold in which the space is not housed. And all the physics, all the differential geometry is based on topological manifolds. If you want to construct a differentiable manifold, it is a topological manifold with extra structure, which is the differential lattice. If you want to construct a complex manifold, it is a topological manifold with a complex structure. If you want to construct an analytic manifold, it is a topological manifold plus an analytic structure. So all the geometry, classical geometry, is built on the assumption that your spaces are housed. Okay?
If it satisfies the scientific condition, that is, it is scientific countable, so it contains global basis. So why we put third condition globally? It is already satisfied globally.
So you want to take away the second condition?
Second condition implies third condition, so I think we should not need third condition.
Second condition, no, this is an independent action system. You can show that these three conditions are independent.
Okay.
And I can give you the reference. If you want, so this is locally Euclidean. And to show that these three actions are independent from each other, you can consult the book of Lee on topological manifolds. And this is Springer. Graduate text in mathematics. I can't remember the name now. But these actions are independent. So if your question is what happens if I erase this, then this theory exists. But these manifolds are complicated because you allow infinity of wells and infinity of trumpets, like this Gabriel trumpet. I don't know if you know it, which is something like, which is a surface which in principle has infinite area. So these topological spaces do not satisfy the second condition, which is second contability.
Professor, in this case, manifolds are smooth or not?
Yes.
Smooth?
Yes. Singularities do not appear in topology. Well, they appear in form of orbitals, but this concept is more complicated. But here, topological manifold, you can show that this is always smooth. Yes. But we cannot talk about smoothing because smoothness is a structural hierarchy. You need an atlas of differentiable functions. And topological manifold does not necessarily have that. But yeah, if you are thinking about the behavior, the global behavior of these objects, you can think that they are not always smooth. Any other doubt? So, which one are the manifolds of dimension 1?
Circles.
And that's a good answer. So, manifolds of dimension 1 are of two types. One is circles, and the other one which is it? Open intervals. R should be a manifold because it is second countable, it is Hausdorff, and it is locally Euclidean. So R is and the circle, the same reason. And the two are different because one is compact and the other not. Do you understand?
Yes.
What are the manifolds, orientable manifolds in dimension 2? Do you know them?
Rectangles.
Sorry?
Rectangles, but in interior, I
Torus.
think they are interior. In interior, they are manifolds. Rectangles.
Discs.
But in boundary, they are not smooth. Therefore, they are not manifolds.
Rectangles cannot be a manifold because they have singularities. So if you take a rectangle, this is not local Euclidean.
But in interior,
The interior, yes.
it is manifold.
The interior, yes. Yes. So manifolds, let me just continue with two dimensions and we stop the topology class there. Manifolds of dimension 2.